Hello. We learned how to handle polynomial regression model, and in this and the second important, maybe it may be more important than polynomial functions. Another important form of nonlinear regression is using the logarithm. So log of x, it is the natural logarithm of x. Usually we consider the base of the natural constant e. But it does not matter. So any log is working well. Okay, so here I'm going to explain the relationship between logarithm and percentage. So it's interesting to see that. Well, I don't think the slides is explaining this well. So let me do it by myself. So first, let's think about the differentiation of a log function. So you know that we know that if you differentiate log of x with respect to x, you get 1 over x. So it's if you don't know how what why it happens, you should memorize it. It's calculus result, and proving this is like it takes too much time. So just take it as given if you don't understand why. So anyhow, the derivative of log is 1 over x. That means, this means, remember, so think about this. So it means that when x increases by 1 unit, the log x increase approximately by 1 over x. That is the meaning of the derivative, right? So when x increases by 1 unit, log x increases by 1 over x. And then so in general, then if x increases by delta x, which may be different from 1, so by delta x, then log of x will increase approximately by delta x over x, proportionally to this argument. So when 1 unit increases 1 over x, so delta x unit increases delta x over x. So you get it. And now let's think about percentage. Percentage when x increases, say stock price, let's say stock price increases by delta x. Say stock price was 200 yesterday, but it increased by 20 points today. Then we say it increased 10% by this formula. So increment is 20, and the reference point is the previous level was 200. So 20 divided by 200 times 100 is 10%. This can be generalized in this form. So x increases by delta x and multiply 100. That's the percentage change. And then we have seen this guy earlier from the logarithm. So then remember, when x increases by delta x, log x increases by delta x over x. So if you multiply 100, it becomes percentage. So extending that idea, you may interpret that 100%, 100 times the derivative of log, you may interpret this as a percentage change, right? So the only difference is multiplying 100. So percentage is 100 times this, and log derivative can be interpreted this way. So, right? So we are going to interpret this way. For example, if log x increases by 0.01, that it means x increases by 1%, right? So if x increases by 1%, log x increases by 0.01. So they are equivalent. Percentage change in x can be interpreted as absolute change in log of x. So percentage becomes absolute value, but you have to divide by 100. Or like proportionally, when log of x increases by 1 unit, it means the underlying x increases by 100%, right? That's this is the equivalent like conversion between log x and x. Keep this in mind, right? Then we can think about three different regression functions. Linear log, log linear, log log. The idea is the same, so but just it depends on where you take the log. You may take log on x or on y or both. So implementation is pretty straightforward. Just you define log of x on theta and regress y on log of x, which is really simple, just like requires two lines. However, interpretation is a little bit more involving. So we are going to study each of them to see how we may interpret and then see where we can use them from like where we can apply those interpretations. So think about the first one. So I will you may read it, but I don't think it's reasonable. Like it's not intuitive enough. So I think it's better to think about the derivative. So you may just read the textbook or the slide, but let me just go directly to the next one. So remember, beta 1, the interpretation of beta 1 is, so beta 1 is interpreted this way. When log of x increases by 1 unit, y increases by beta 1 unit, right? That is the interpretation of beta 1. And remember, I said log of x increases by 1 unit. And earlier we learned log of x increases by 1 unit is equivalent to increase in x by 100%. X increased by 100% is log of x increased by 1 unit. So therefore, now you may interpret this beta 1 this way. When x increases by 100%, that means when x doubles, y increases by beta 1. Or equivalently, when x increases by 1%, y will increase by beta 1 divided by 100. You get it? So 1% increase in x, 1% increase in x implies 0.01 increase in log of x. Like here, remember, so x increased by 1% means log of x increased by 0.01, and then y increases by 0.01 beta 1. That is how we interpret this, right? 1% increase in x means 0.01 increase in log x, and which means 0.01 beta 1 increase in y. So you need another step of conversion, converting x between x and log n. So then why does it make sense? Yes, I think so. So for example, if think about income, without taking log, without log, what we considered is, so we considered additional dollar. Like say, I give you additional $1,000. However, I told you that $1,000 could have different value to different families, different households. Like to poor household, $1,000 will be super valuable, very valuable. However, to say Bill Gates, Warren Buffett, like Jeff Bezos, like giving $1,000 to them is nothing, right? So then the $1,000 is not comparable, like between different families. So their effects will be different, which is a problem. Instead, we are going to change this. Say I will consider 1% of income. 1% of income. So if my household is making like only like $10,000, I will give you 1% of that, like $0.1,000. But if there is someone who is making $100 billion, then I will give them $1 billion. So I will compare $1 billion to a billionaire and $1 to a poor family. These, even if their absolute value, absolute size is very much different, but their actual implication could be more comparable to each other. So that is the meaning of this. So we are considering 1% increase in income, not a certain amount of dollar. So you have to think which is a fair increase, like a uniformly comparable change in income. I think it's obvious that obviously 1% percentage change, constant percentage change will be more fair when you compare poor family and rich family. So then I would take log on income. That is the interpretation and how we use this model. And then interpretation is, so log income, the coefficient is 36. Then this means when your income doubles, test score increases by 42 points. Or when your income increases by 1%, the test score will increase by 0.3642 points. So that is how we interpret this coefficient. Additional thing here. The log, like the intercept is, remember, the intercept is the value, the expected value of test score when this part is 0. This part equals to 0 when income equals to 1, not 0. So when income equals to $1 or $1,000, so exactly the test score will be predicted as 557. So this part equals to 0, log of x equals to 0, happens at a different value of x. It's not x equals to 0. And all, like, so implementation wise, everything is the same. Like implementation, how we calculate standard errors, how we calculate R-squared, how we calculate confidence intervals, p-values, all the same. So you may use the same command, regression command. There is no difference in calculation. So how does this compare to the cubing model? So usually the log model is preferred because it has a better interpretation. Cubing model has no economic justification. Why? Why does it have to be cubic term of income? Why not fourth order or higher order? Or why not only quadratic? So there is no background, but logarithm is preferred because it has a clear interpretation and easier to interpret. So that's simple comparison. But sometimes cubing model may be better, but good luck with your interpretation. So that's usually where it matters the most. Here it is. So they are similar. In the end, they are similar in terms of their fitting, but so the fitting wise, purely like mathematically, they may be similar, but interpretation wise, absolutely the log model is better. So keep that in mind. So I'm going to stop here. We'll continue log linear model in the next video. Thank you for watching. See you later.